Hello, my name is Leanna, and I will be showing you how to do question 2 of the 2013 Calculus BC free response questions. This is going to be a question primarily about polar. They give us the curves r equals 3 and r equals 4 minus 2 sine theta, and also that they intersect at pi over 6 as well as 5 pi over 6. This makes the problem a bit easier. If they did not give us this, you could also set the two curves equal to each other and solve for theta. Now, question A asks us for the area of the shaded region within the graphs of both curves. So to solve this, we are first going to separate them into two sections. The first section in green is the part where 4 minus 2 sine theta is closest to the center, and the second part is where r equals 3 is the graph closest to the center. Now, first we are going to solve the green part. To find the area of a polar section, we can use this formula, 1/2 times the integral from one intercept to the other intercept, which in this case is pi over 6 to 5 pi over 6 of the curve 4 minus 2 sine theta, all squared d theta. You could also go from the first intercept to the midway point, as this graph is symmetrical, which would be pi over 2. In that case, you would do 2 times 1/2 from pi over 6 to pi over 2, as we're doubling the area from pi over 6 to pi over 2. Both of these will result in the same answer. The second part is the pink part, which can be solved in two ways. The first way, we can recognize that the pink part is 2/3 of the full circle, and as the area of the circle is 3 squared, or 9 pi, we can simply multiply those values and get that the area of the pink region is 6 pi. You can also use the same formula as for the green part, where the first intercept is negative 7 pi over 6, all the way to pi over 6, 1/2 of 3 squared theta, which also gives you 6 pi. In this case, one of the points for the grading comes from the constant, the 6 pi, as well as the limits of the integral. So even if you don't know how to solve the whole problem, we do know that information, so make sure you put down all the information you know. This applies to this problem as well as any other AP problem. So if you put those together, you can add. And now coming to the calculator, you can see I've inputted the integral, making sure to remember the 1/2 at the beginning, as well as adding parentheses around the radius, ensuring that you're squaring the entire thing rather than just the x, as it could be a problem that you're squaring the wrong things or inputting it into the calculator incorrectly, which would be an unfortunate way of losing points. Also adding 6 pi, and then if we click enter, we can see that the result is 24.709 or 24.708, which is cut off at the third decimal instead of rounded. For question B, they are looking for the x-coordinate of the particle on r equals 4 minus 2 sine theta. So, as you should know, x is equal to r cosine theta when converting from polar to Cartesian. So x equals 4 minus 2 sine theta times cosine theta. And we also need to change the theta to t squared because they're looking for the time. So x equals 4 minus 2 sine of t squared cosine t squared. And we are looking for when the x-coordinate is -1. -1 equals 4 minus 2 sine t squared cosine t squared. And you can move the 1 to the other side, get 0 equals, let's see, like r cosine theta plus 1, where our cosine theta is that value that we found. We can plug this right into the calculator. Here at the calculator, you can see I've plugged in 4 minus 2 sine of x squared. X and t are interchangeable in this case, times cosine x squared plus 1. It was important to move the 1 to the other side because we want all of this to equal 0, which means that when we graph it, as you can see, we are looking for when the value is equal to 0 from the conditions at the beginning. You can see it's from 1 to 2, which means that you can just input the start and the end and see the x or t equals 1.428 or 1.427 with the other digits cut off. And that is our answer for when the x-coordinate of the position is -1. Now finally, for part C, they're looking for the position vector. So the nice thing is we already have the position vector for x. You can write that out. 4 minus 2 sine t squared cosine t squared. Now we are just looking for y. So y is just like x, but it's r sine theta, which means that y equals 4 minus 2 sine theta cosine theta, and y equals 4 minus 2 sine t squared. My apologies. They should be sine theta and sine of t squared. And that will be our answer for the position function. Secondly, for the velocity vector, the velocity is just going to be the derivative of the position function. So we take the derivative of x and the derivative of y at 1.5. And the lovely thing here is that your calculators can take the derivative at certain points. Here at the calculator, to find the derivative of a function, you go to math and number 8, which is the nth derivative. And here you can input your function. And then at 1.5, click enter, and that will be our x-coordinate. And you can do the same thing for the y-coordinate. At 1.5, click enter, and that will be the y-coordinate. At t equals 1.5, the velocity vector is going to be -8.072 and 1.673, or -1.672 when cut off. So this is our position vector, and this is our velocity vector. If you are looking for additional ways to practice and for more information, there are a few videos that you can look at. If you're looking for specifically the area between two polar graphs and incorporated by both, you can watch the video The Area Between Two Polar Graphs from Khan Academy on YouTube. For a more general and longer video on the area of polar curves, you can watch the video Finding Area Bonded by Two Polar Curves by the Organic Chemistry Tutor, also on YouTube. Some practice problems you can look at are from, if you look up Paul's online notes called Area with Polar Coordinates. Practice problem number 6 is pretty similar to this one, though all of the problems on that page will be helpful for practice. If you are struggling to convert polar to Cartesian, as we had to do in question B, you can watch the video How to Convert Polar to Cartesian Coordinates by Anil Kimar on YouTube. The important part is from 0 seconds to 2 minutes and 30 seconds, though you may also do the problems after that for additional practice. Finally, for position and velocity vectors, you can go to page 751 of our online textbook, which is in Unit 9.5. Examples number 6 and 7 are pretty good practice that are quite similar to these, where you're finding the derivatives of vectors, which are often the velocity and acceleration vectors. So you can check out those problems in those videos. I will also link those in the description of this video, and I wish you luck.